Welcome to the Mechanics of Solid lecture series. Here we work our last example on indeterminate axial systems. And here's the problem we're going to work. We recognize this as axial members connected to a rigid rotating member. We have the rigid member in the vertical direction with a load P equal to 25 kilonewtons applied at the top, rotating about a hinge at the bottom at point A, and then it's connected to two intermediate axial members, member 1 with a length, cross-sectional area, and elastic modulus as given, and member 2 with a length, area, and elastic modulus as given. We're also given the relative lengths between the members and the top of the rigid beam. So we've dissected all this information for you. And we're asked to, for this bar assemblage, find the internal stress in bars 1 and 2 and the deflection at D. So let's go ahead and synthesize that. What we're asked to find in this problem is simply the stress, sigma 1 in bar 1, sigma 2 in bar 2. Because these are in standard SI units, we're going to find our stresses in units of megapascals, or Newton per millimeter squared. And then we're also asked to find the deflection, which I'm going to at point D, which I'm going to call VD, and we'll find that in units of millimeters. And to give a sketch of what that means, as the force P pulls, the bar will rotate, and the total deflection at the top, V sub D, of course, is a greatly exaggerated picture. We recognize this an example of rigid or axial members connected to a rotating rigid element. Okay, and in this type of problem, we will always proceed by drawing a free body diagram of the rigid bar itself, where we have made cuts through the axial members. So we're going to replace those axial members with unknown forces. So our rigid bar will look something like this. The pin at the bottom can be replaced by reactions AX and AY. The bar 2 we're going to replace with a force, which I'm going to call F2. Always going to draw in tension, even though it might not be in tension, but just for consistency. The force F1 in bar 1, also drawing in tension. And then here's my P equals 25 kilonewtons. My relative lengths between the members, I have 410 millimeters, 410 millimeters, and I'm sorry, 420 for A and B, and length C 510 millimeters. Okay, so what I want to find here in order to find the internal stresses F1 and F2 is I want to find those forces themselves. So I don't need to find AX and AY, and the most direct way to find these internal forces for my equilibrium equation is to do a sum of the moments about A. So for equilibrium, I have one equation. I'm going to do the sum of the moments about A equal to 0, taking moments to be positive in the counterclockwise direction. I'm going to compute my moments in kilonewton millimeters because most of the knowns are given in those units. And starting from the bottom and working up, I have a moment negative F2 times 420 millimeters. I have a positive moment F1 times 840 millimeters. That's the sum of A plus B. And then I have a negative moment P, 25 kilonewtons due to the force P at the top, times the total length, which is A plus B plus C, 1350 millimeters. Set that equal to 0. And just noting that this quantity, if we calculated it out, is 33,750 kilonewton millimeters. I'm going to leave the equilibrium equation in that form for the moment and move on to a new sheet to draw my compatibility equation. Okay, so for compatibility, I need to consider the deflection as in each of these members as the bar rotates. So I'm going to draw the rotation of the bar, something like that. And I have here that as the bar rotates, point B moves over by some distance v sub B. Point C moves over by some distance v sub C. And point D moves over by some distance v sub D. And then, of course, I have these lengths between my members, 420, 420, and 510, all in millimeters. Okay? So using similar triangles, I can write the relationship between the deflections, and that is my compatibility equation, or my compatibility consideration for this particular problem. First triangle is this small one here. So I'll say V sub B over 420 mm equals the second triangle, V sub C over A plus B, 840 mm, also equals the largest triangle, V sub D over that total height of the bar at 1350 millimeters. Okay, and based on this, I can make a couple of observations. First of all, that V sub C equals 840 over 420 over or 2 times V sub B, and I also observe that V sub D equals 1350 over 420 or about 3.21 V sub B. Now I need to relate these total deflections to or movements to the internal deflections in my bars, and I can also note that as point B moves over, bar 2 shortens by an equivalent length. So I would say that delta 2 equals negative V sub B. In other words, if V sub B is positive, delta 2 is going to be negative. And likewise, I note that if point C moves over, then bar 1 will also elongate by that same amount. So delta 1 is equal to V sub C. Okay? So from this equation right here, I will rewrite that in terms of the internal bar deflections. Simply delta 1 equals negative 2 times delta 2. We know that the deflections are equal to FL over AE. I'll write that as F1 L1 over A1 E1 equals negative 2 F2 L2 over A2 E2. And this is the compatibility equation that we want to work with to go further. We'll continue our calculations in the next video.